Hello, everyone, and welcome to our Mechatronics Education Community webinar, in which Dr. Kevin McFall, Interim Chair and Associate Professor at the Department of Mechatronics Engineering at Kennesaw State University, will share experiences from developing a mechatronics-specific computing course. My name is Zuzana Fabusheva, and together with Dr. Nima Lotfi from Southern Illinois University, Edwardsville, we will be your hosts and webinar moderators today.
All right, thank you very much, Zuzana. Hello, everyone. I would also like to welcome you to our today's webinar. Today's webinar is one of the webinars that we've had in the past 2 years in webinar series for the future of mechatronics and robotics education. Today, I'm honored to introduce Dr. Kevin McFall. Dr. McFall has bachelor's degrees from Virginia Tech, master's from MIT, and a PhD from Georgia Tech. Before joining academia, he had worked for 10 years overseas in Sweden, Japan, and France. And at 2008, he started his academic job in Penn State. Since 2012, he has joined the Bachelor of Science Mechatronics Engineering program at Kennesaw State University. And he's now the interim department chair and associate professor in this department. His research interests involve applying artificial intelligence and machine learning to autonomous vehicles with his undergraduate research student. He has been instrumental in developing the curriculum for this program and coordinating program assessments for ABET accreditation. I'm really excited to have Dr. McFall as one of our presenters today, and I don't want to keep him longer. I want to pass the microphone to him. So I'm looking forward to listening to your talk, Dr. McFall.
Wonderful. Well, thank you so much, Nima. Welcome, everyone. It is very fun for me to be here today. My students, they're kind of a captive audience. You guys have taken time out of your busy days to come and talk to me, so hopefully I can live up to sharing something that will be of interest to you today. As the title says, I'm going to be talking about how we created a mechatronics-specific Computing 2 course in our Mechatronics Engineering program. In order to talk about this Computing 2 course, I need to give you a little background about our program. We started in 2007. We have about a little over 400 students in the program now. And here's sort of a breakdown of all of the different courses in our program. You can see we have 28 credits that are mechatronics specific. We're really fortunate to have our own department of mechatronics engineering, so we control these 28 credits completely. Of course, we have service courses in electrical engineering and mechanics, computing, of course, that's the main topic today, general engineering, math, science, etc. So this Computing 2 course, originally, it was a course that was delivered by the computer science department. And over time, I'm going to talk a little bit about the history here, about how we ended up controlling that course and how that's been a really good move for us. So back in fall 2013, at that time, we had this computer science run first level computing course and the second level computing course, this object-oriented C++ for engineers. It was a course for us engineers, but it was taught by computer science faculty in the computer science department. And in advance of our ABET accreditation, we were a little short in our math, our 32 credits of math and basic science. So it was a bit of a scramble then, realizing that we were short, and poor Computing 2 ended up drawing the short straw, and it got jettisoned from the program at that time to make room for the math electives, so that we could have a successful ABET visit. In that next year, we kind of realized, well, yeah, all right, fine, we survived ABET, but we really need our students to be pretty strong at programming, and maybe we needed to find a way to bring that back into the program. So 3 of the courses that were required in the program, we decided to make to no longer require them, and replaced them with 2 technical electives, and then this Computing 2 course. So at that time, before this change, all of the courses in the program were completely prescribed. The students had no choice. So, I mean, these courses here in red, I mean, they're very good courses. We liked them and they were good for the program, but something had to give. So, you know, they could be absorbed in the technical electives. Students could choose 2 of those or other classes actually. But there was a chance for us to bring that Computing 2 class back into the program. And actually, interesting story, you know, the name of the program was not Intermediate Programming for Mechatronics. At the time, we were a little concerned that computing would feel like we're stepping on their toes by teaching a computing course in our engineering college. You know, computing is not even in the same college as engineering here at Kennesaw State. So we kind of did a little smoke and mirrors. We called the course Engineering Algorithms and Visualization. I don't think we actually fooled anybody with that. I don't know, but we were a little worried that, hey, you know, we're going to be teaching a computing class here. And in the end, I think it turned out well. And our computing colleagues were gracious enough to give us the space to try it. Then later, of course, we didn't like that engineering algorithms and visualization. We really wanted to emphasize that it was a programming course, so we changed the name to its current name here. Now, one of the immediate effects there was that we were allowed to teach MATLAB in that course. Previously, you know, that was a computer science course. We were not the only ones that took it. We did not control it, so we didn't have direct control over the content. So luckily, what we were able to do is to teach some MATLAB, which there was a following course in our program, Mechatronics Engineering Fundamentals, where we taught MATLAB, but now we could move that MATLAB content into our Computing 2. That freed up some space in our Fundamentals course, and we were able to add in microcontrollers and programming of microcontrollers, which was not in the program before. So that was an immediate benefit to us being able to control that Computing 2 course, that we could sort of tailor the content and be able to find ways to get the things that we wanted to be in our program. So I don't mean for you to read all the text on this slide. Basically, you know, this is the catalog description for our Computing 2 course, this intermediate program for mechatronics. And this is the catalog description of the current Computing 2 course that we have at KSU in the computer science department. Now, you look at, I've highlighted the things I want you to sort of focus on. And, you know, these red topics, they're all great topics. I mean, just like electric machines was a great topic that ended up being, you know, an option in a technical elective. But, you know, there's so much content you want to get in the program. There's, you know, only so many credits. There's a push to get as close as we can to 120 credits. So yeah, it's great to learn about parallel programming and database programming, but hey, isn't analog sensors and digital sensors and visualization of data and pneumatics and motor control, aren't those things more important for mechatronics engineering students than event-driven programming? I mean, these things are important, but you know, you got to make difficult choices. And you know, I would argue that this course here fits a lot better in what we really want our mechatronics students to know. It'd be great if they can get this stuff over here, but this stuff is more of a core for what we're hoping our students to be able to have as in their skill set. So I want to give a little bit of an idea about where the programming happens inside of our program. In our freshman year, they take their first programming course that is still run by the computer science department. This is actually the first programming class, Computing 1 course that their computer science students take. So our students are taking the same Computing 1 as computer scientists that then feeds as a prerequisite into our intermediate course, the one I'm talking about today. Another important piece is that we have Calculus 1 as a prerequisite to our intermediate course. And by doing that, we know that our students have a certain mathematical sophistication, and we can do applications for the programming that are specific to you know, mathematical modeling, and I'm going to give you some more examples. But to me, that's a big difference. You know, there's no, you know, you have no guarantee of what math students have in that programming 1 course in the computer science department. We can expect our students to be somewhat math savvy in ours. In our freshman year, our students take not only that computing 1, they have a robotics project that they do in their intro to mechatronics engineering, and do sort of graphical block programming. This class they take in their first semester, and so it's sort of drag and drop. It still loops and that sort of thing, but we don't have any prerequisites that they have any computing skills. So first they learn how to do this graphical block programming. Probably second semester they take their computing 1, and in their sophomore year they'll get into the intermediate programming. Now, what's really important is we control this course now, so we can make sure it has the content that is going to feed as prerequisites to some of our later courses. Our fundamentals course, there's some mobile robotics where they use a C++ object-oriented library, so they need to know something about object-oriented C++. They use MATLAB for some calculations. They do their microcontroller programming in C. Then also in the senior year, there's a robotics course, and very heavily relies on robotics toolbox and MATLAB. So we need to make sure back here that they have a good background in MATLAB to be prepared for that. We also have another course that has a significant programming piece. That's our instruments and controls class, where there's some programmable logic controllers in there, and they're writing their programs in ladder logic. So that's not sort of in the same pipeline of the computing as digital logic as a prereq. But I just wanted to give you a little of an overview of where the coding shows up in our courses. But these 2 classes here are the only, you know, meat and potatoes. The main purpose of the course is to teach you coding. So yes, this is a mechatronics course, and we will use mathematics and engineering topics, but the whole point is to get the students to be better programmers in this course. It really is a programming class, really, and not, you know, so much of an engineering course. So that course has a lecture component and has a lab component, you know, it's still a work in progress. I'm still not completely happy with exactly how it is, and the main thing I'm still a little worried about is it feels a little schizophrenic in this course, because we cover object-oriented programming in C++, builds upon the C++ they learn in their first programming class. We talk about MATLAB, where we do data visualization, matrices, that sort of thing, and we also introduce Python, which is becoming much more common nowadays, and we definitely want our students to be you know, to be current with that. And we cover NumPy and Matplotlib, which, if you know anything about Python, basically they ripped off MATLAB, and much of the syntax and the functionality is the same as MATLAB. So even though Python is a new 3rd language that's covered in the course, it's really doing the same thing. It's more or less translating the MATLAB stuff into Python. But like I said, I'm still open to, you know, maybe we do our object-oriented stuff in Python and leave C++ in the first course. But we'll see. It's still a work in progress. But the really important thing that I really love about this course is that the application topics that we have here are all mechatronics related, because we've got that calculus piece there, because these are mechatronics engineering students. You know, we can go over applications that aren't just, you know, the Rolodex that you see in a computer science class, or, you know, doing a database query on, you know, addresses. You know, they're doing things that are mechatronics, they're engineering related in their applications, even if it's really all still about learning to be better programmers. Especially in the laboratory, we try to put as much as we can into hardware, so they're seeing breadboards, switches, LEDs. Again, we need to be careful in this course. The whole point is to learn programming. So, you know, there's no prerequisite for electronics or anything like that. And we try to make the hardware as simple and straightforward as possible, so they can really focus on the coding pieces. So here are some of the application topics, and I'm going to show you some examples, both of the homework problems in the labs, as we go on a little bit farther in. So again, the main thing is you're teaching programming, you're trying to increase their programming skills, but doing it in a way that is application specific to mechatronics engineering. And that's what I really like so much about this course. So here's an example of one of the homework problems. This figure, I ripped it right out of the dynamics textbook that they use. And here's, a human cannonball gets shot out. It's basically, a projectile motion problem. So, we don't teach the students about dynamics. We don't tell them, I'm not deriving anything. We present, hey, look, there's a guy coming out of a cannon, and as time progresses, his X and Y position change in time, and here are the equations. Okay, and so we give them these equations. I say, okay, well, depending on the angle that you shoot this guy out, the height that he ends up, the maximum height he ends up is going to be different depending on that angle. And the amount of time that he's going to be in the air is going to depend on that angle. And how can we write a program to be able to calculate the max height he has and the amount of time that he's in the air for different values of this angle? These are important things that we might ask. Now, of course, the savvy students are going to have maybe already taken physics 1 or so, and they may be able to solve this problem analytically, which is fine, and I let my students solve them analytically if they want to. But really the idea is to give them another option. Hey, what if we solve this numerically? What if we plug in discrete values for time and calculate discrete values for X and Y? We have some sort of loop, or in MATLAB you can do it with element-wise operations. So, we're going to code this solution, and we've got all these different X and Y values, and let's see, well, where is the largest Y? And well, that requires having to look through a series of values and pick out the maximum. That's a coding technique that you need to learn. Okay, and then what is the time? How when is the time? How long has he been in the air? So, well, how do you find numerically how long he's been in the air? Well, you watch the Y values. He's going to go up and he's going to come down, and once he passes Y less than 0, okay, that's when he's hit the ground. Okay, and so then the students have to go through. They've got this series of X and Y values. They have to go through and find, well, at which index value does Y go from being a positive number to a negative number? And then I need to go back and look at that same index value in this array of times. You can see, this is like searching through a list of values, pulling out a list, comparing it to another list of values. These are all programming concepts, but it's related to something engineering that they can get their, sink their teeth into. And then, of course, doing this in MATLAB, we can, plot these values, and we get this idea of taking an equation and working out the details in code to be able to visualize what it looks like. You've got two different axes, one value is on one axis, a secondary axis, so there's a lot of, that's why we called it engineering algorithms and visualization to begin with. So, we get the data visualization piece in there. Here's another problem that I gave for homework, and the idea here brings in a bunch of curve fitting and some other things. Basically, the students are given position and force data values. Now, of course, they're all sort of synthetic. I just added some noise in there. But the idea is they've collected some data for X and F values, and all of these data points, as you get too high, you end up in this nonlinear region. And if we want to use this data to find what is the spring constant, we need to make sure we ignore the nonlinear region. So how can we do that sort of automatically in the software? So I give them an equation here for how we calculate the slope of a curve given multiple data points, assuming that that goes through the origin, because we know that's something we know about the data. And so here's an equation. Here's a mathematical equation that they need to use code to calculate something. So that's a difficult piece for the students. I got this mathematical model and I want to put it in a computer code. There's this summation and all this mathematical notation. How do I get that into a computer? Well, it's a for loop. You got to loop through. We've got as individual value X times the individual value F. I need to store that in a temporary variable. Then I need to loop through again and add the result. You can see there's coding, really coding relevant questions involved in here. So the idea behind this is we'll use all of the data points and we'll calculate the slope. And then we'll calculate a correlation coefficient. It's going to be pretty good, but it's not going to be great. And then we'll take away one data point, calculate a new slope, a new correlation coefficient. Take away another data point, a new slope, a new correlation coefficient. You keep doing that through a loop until you get to the point where, hey, the correlation coefficient's not increasing anymore. It's not becoming a better curve fit. Maybe I now have gotten outside of the nonlinear region and I can go ahead and use the slope here to estimate my spring constant. So again, there's multiple loops going on here. There's nested loops inside of here. You're looking through values. You're comparing things, element-wise multiplications. There's computing concepts going on in here, but it's not a computer science application. It's a mechatronics application. We can start getting our students savvy about understanding the mathematical notation, how that model translates into something that we can calculate with the help of a computer. So it's really fun to do these sort of things. Here's another example of a homework problem. This guy here is taken from a strength of materials textbook. So we've got this, this channel, and we take a cross section and we apply a bending moment to it. And what is the stress at the different positions along the cross section? Again, they don't need to know anything about strength of materials. You give them the equations. These are all end up being constants. Here's an equation. Here's the dependent variable depends on the two independent variables y and z, and all the others are constants. So it's a mathematical equation. They don't have to understand where it comes from, but it helps them see, oh, well, I'm programming something that's helping me, and when I get to strength of materials, I might be able to use this computer to help me in my calculations in that class. So sort of gives them a preview of things that they're going to see later in the program. So they have this equation, and the whole idea is, well, let's plot what is the stresses as a function of y and z position in the cross section. And it's a three-dimensional surface plot. And just plotting that three-dimensional surface plot in itself is not all that difficult, but an extra piece in this problem is, well, there's this hole in the middle of the cross section, and we don't want to include that in the plot. There's no material there, so there's no reason to display the stress on there. And in MATLAB, the way you can make that happen is you just set the values at that part of the matrix to be not a numbers. And anything that's not a number doesn't get displayed on the screen. So then the students have the question, well, how do I identify the region in this matrix to be not a number? And so then it comes down to, well, you could hard code it. You could look at the values, say, oh, well, that's row number, whatever, but you can challenge them. Well, let's do this automatically. You can use logical indexing. Well, you could use numerical indexing. You can use logical indexing. You can compare, use logical indexing to look at whenever y is greater than some amount and y is less than some amount. And if you're talking about programming, you introduce numerical indexing versus logical indexing, the students might not get it. What do you mean? Why do I need both of these kinds of indexing? And here they get to a problem where they see, oh, instead of finding the index numbers, I can just say, well, find the locations where y is greater than something and y is less than something and z is greater than and z is less than. And then they see, oh, logical indexing, it's so much easier than going through and saying, oh, where is the number where that value happens? So, the students get a much deeper understanding of why we're trying to show them all these computing techniques and how they can be applied to what they're going to be doing in their program. So the labs, I think, are really the most fun piece to this, and I really had a lot of fun trying to develop the labs. This little guy, it's from a company called Fisher Technique. It's electro-pneumatic trainer, sort of a kit, and it's really great because it has so many different pieces to it. We end up not using their proprietary controller. Inside this control, it has the motor controllers, it has pull up and pull down resistors, it has sort of built in the electronics, and it's nice for us to at least introduce our students to that. So we replace this with an Arduino. We have a little breadboard to put our H-bridge motor controller on so that students get to see an integrated circuit, how that goes in a breadboard, how you wire it up. Again, you have to try and keep that as much as you can, as easy as you can. It's not a breadboarding and hardware course, but it's really cool for the students to see I'm coding this stuff and I'm making things happen in the real world. That's really fun. So you've got an Arduino here, and we've got limit switches. So we've got a digital input, and there's a photo transistor. That's another digital input. We've got a motor encoder. That's another digital input. Then we've got an analog input. There's this color sensor. Basically, this thing is going to pick up these little pucks and put them on here to determine what the color is so that they can put it, sort them in the right bins. So we've got this analog sensor. We've got an analog output. There's a solenoid here for making the suction happen on the tip of this robotic arm. There's also another solenoid back here, can't really see it, that makes the arm go. So that's a digital output. We got digital inputs, we got digital outputs, we got analog inputs, we've got the DC motor, so there's a PWM output. So we've got all of the pieces on this pneumatic trainer kit, and we spend about a month or so working on this, four or so lab periods working on this, and it's really cool because in the end the students end up getting this robot that they've programmed to move. Now, I can't claim credit, this is not my video, I found it on YouTube, but it shows pretty well how things work. And it goes over there, checks what the color is, depending on that, it moves a certain amount to the positions. There's an encoder in there, so you know, oh, well, if it's white, I only need to go 5 steps. If it's red, I need to go 6 steps. If it's blue, I need to go 7. There's the little limit switch here, so that's how the motor will keep going until it gets to the limit switch into its home position, and then the phototransistor will pause unless that beam is broken. So you can see there, all these pieces all go together. You have all of the important analog inputs, digital inputs, analog outputs, and PWM outputs, all on this nice, tasty package, which I find is really, really cool. So, like I said, we spend about a month or so working on this, and then we have some other projects. Do a little PI control lab. Again, they haven't taken control systems, but it's not that hard to convince them, well, look, I've got this IR sensor that's going to sense some distance to an obstacle, and the larger that distance is, the stronger we should turn the motor. It's a pretty, you can give that sort of an intuitive argument for what proportional control is. So this little robot, you can see I built it out of a bunch of spare Vex Robotics parts. The motor, I didn't do a very good job with this picture because the motor is sort of hidden on the back side, but I use these old Vex motors I've got kicking around. It's nice they actually have a motor controller built into them, so they don't have to worry about the motor controller. We got a battery on here to run the motor, got a little breadboard to make all the connections, the infrared rangefinder, and then our Arduino. And so here is a little example. The students in a 3-hour lab period can put this together and put a little proportional controller on there and make this robot move back and forth. And then if they've got some time, we can start talking about integral control. Pull up on the serial monitor and display what the error is. And what you'll see is, if you hold that barrier steady, the robot will move and stop. But if you look at that error that's being reported on the serial monitor, it's not quite 0. There's a steady state error. So, well, then you can go in and put integral control. Well, how do you do that? Well, you just keep, every time through the loop, you just sum together the errors and you add that into your control signal. And that's intuitively not too difficult to understand. And then you can show, okay, now we put this I piece into the PI control. And now if you wait long enough, you can see that it will drive that error down to 0. So, this is a sophomore level class. They haven't learned about all the theory about these things, but they can program them and see them happen, in physical embodiment in the lab. And the students really appreciate getting to build this stuff and do these things and see them happen. And I really hope that it's giving them inspiration when they do get to the theoretical aspects of these concepts in their later courses. It gives them more motivation to dive deeper into them. Here's another lab that we do. This one doesn't have any hardware. But I give them a video feed here of me kicking a ball, and they do a little image processing here. It's nice, and MATLAB has a little built-in function for detecting circles in your image. They have to do a little tweaking of the parameters there. And then they analyze a video feed. I mean, this is really interesting to the students. Hey, I can do a little image processing, and I can read a video. Well, it's not that hard. I just take one image, and I analyze it, and then I take the next image, next frame, and I look at it as a single image. And then you do that over and over, and I identify, tweak all of the parameters of this find circle command, and I can identify all 4 of these balls, because if I'm going to follow the one ball that's moving, I need to know from frame to frame, which ball is moving and which is not, so that I can figure out, where that ball's going. Now, the end result of this lab isn't just to identify the balls, but to use this video to estimate the speed of the moving ball over time. So I've got a little tape measure in here so they can measure, oh, this is 1 foot, and we can see, well, how many pixels across is it for 1 foot? And then they can be able to convert pixel dimensions in the image to physical dimensions. And then they know, oh, well, this is 30 frames per second, so I can calculate then what the amount of time between each frame is, so I can match the position of this ball to a pixel position in frames and convert that to physical positions in feet versus time. And I can produce a graph here of the speed of the ball as a function of time. And if you break this down and put it into little digestible pieces, these sophomore level students can do each of them, and it's a really rewarding experience for them, that they can come out of this. I analyzed video, I did image processing on video, and I tracked this ball in there, and I can calculate what its speed is as a function of time. Really, really fun stuff, and really focuses why the programming is necessary. They might say, oh, I want to do that, but how? You need to be a good programmer, and we're giving them those programming skills in this course. All right, so that Computing 2 course, it used to be in computer science. We moved that over to the Mechatronics Engineering. I'm a really big proponent of trying to rely as little as I can on these service courses in these other departments. I mean, it's great. I mean, like I said, all those topics that got lost from Computing 2, they're important, but man, doing these other things are a little bit more important. So, I'm still looking at ways that I can rely less on these service courses. For example, that fluid mechanics class, we were already sort of doing this, offering a special topics course in fluid power and letting our students do a course substitution for fluid mechanics. Here we can concentrate on hydraulics and pneumatics. Yeah, we still do piping systems and friction factors and those sort of things, but maybe we don't need channel flow, and maybe we don't need some of the pieces that are in here, and we can replace them with things that are a little bit more relevant for our mechatronics students. We're looking perhaps at not having our electronics course anymore be a service course. We're already teaching some electronics in our fundamentals. Maybe we can beef that up a little bit, cover op amps in there somewhere, absorb the important pieces of that electronics in our courses that we do control, so that we can make space for, more PLC rather than just one course. Maybe bring in some robot operating system stuff into the program. Find places where, yeah, that whole course in electronics is useful, but some pieces are better useful for mechatronics students with some other topics. We're even thinking about taking our engineering economics course, roll some of that time value and money stuff into our senior design class instead, so we can make way for a machine learning course. That's especially would be great to have as we move forward for more automation and AI. So, I've just really been so excited about that Computing 2 course. I feel like it serves our students much better than one developed by computer scientists for computer science majors. We can be a little bit more effective in getting the mechatronics content that we want our students to have. And I think there's opportunities in some of these other places to, really look at what is the core content that we want in our mechatronics program, and how can we fit that in, because we have such limited space in terms of credit and time with our students. So that's what I've got in terms of formal presentation here. I don't know, maybe some of you guys out there have some questions that I can answer. I don't know, Nima, have you got any questions out there from any of the folks?
Yes. Actually, we have one question. First of all, I want to thank you for this exciting presentation, because to me, this is one of the things that I've been trying to incorporate into our own curriculum that we have on mechatronics and robotics engineering. And exactly as you're excited, I'm also excited about a course like this. Of course, mine is not as well developed as yours, but again, it's a work in progress. So I try to include all these fundamental aspects to the course. So thank you for that. So I'm going to ask the first question, and then I also have some questions. So the first question was about MATLAB to first-year students. Which topics do you think are the most critical ones?
So you're saying in terms of for first year students, I mean, we don't cover MATLAB in the first year, but you're saying if you did cover MATLAB in the first year, what would be the most important topics?
Yeah, the question is like that. Yeah, if you were to teach MATLAB for first year students.
I personally don't have a problem teaching MATLAB, doing the Computing 1 course in MATLAB. But I kind of do like having the Computing 1 served by the Computer Science department, because I mean, if you have an engineering faculty member teaching computing, perhaps they're not quite as good at delivering the things about memory management and variables and all of the really fundamental pieces. Where do these variables live in memory? What is a loop, and how, what is the abstract idea about a loop? Okay. So I personally like a CS approach for the first class, but you could do that in MATLAB, but I really want that first programming class to lay the groundwork to really understand coding and programming more than the applications. I really think you gotta really get that base in computing before you start laying on the applications.
Okay. So
that's
the
my
second.
personal.
Okay, got it. So the second question, which is like in line with the first question, is okay. So in the sophomore year that you have this intermediate programming for mechatronics, MATLAB, do you just cover MATLAB, or do you go into Simulink as well?
We do not do Simulink in this course. Simulink gets covered later. I didn't actually put that in this group here. We have our control systems lab covers Simulink. Our intermediate programming course isn't a prerequisite for that, because making Simulink work and putting all the blocks together, it doesn't necessarily require line by line coding, so we haven't made it a prerequisite. But Simulink lives in our control systems lab. And again, luckily, we control that. Our control systems course is in the mechatronics program. This is a separate course from what the electrical engineers and the mechanical engineers do. So we can make sure that Simulink has somewhere to live, and that's in our controls lab.
Okay, thank you. So we don't have other questions yet, and I had a few. So you're aware of our efforts towards basically reshaping the future of mechatronics and robotics engineering. You
Right.
attended our first workshop in Atlanta, and one of the common concerns with faculty was this exact same topic, is that our mechatronics students need more exposure to programming. And just one computing course offered by CS is not necessarily enough. However, if they want to take more advanced courses like software engineering, they would require a lot of prerequisites that CS requires. But our students don't necessarily take them. So what is the trade-off? How can we go about providing that experience, especially in regards to intermediate or advanced programming? So object-oriented programming is one of these, and building on that, especially with applications in mechatronics and robotics engineering. So for this course, what kind of resources are you using in terms of textbooks, or have you developed the whole thing from scratch?
Yeah, I developed this course from scratch, and it's actually a no-cost course. That's a big thing here in Georgia for identifying courses that are low cost or no cost. I identified some freely available online textbooks in C++, in MATLAB, and in Python. So they have some textbooks that they can refer to that are free. But all of the homework problems and all of the lab exercises I developed completely from scratch myself. So I don't really follow the textbook, but they're there as a resource to the students if they want to go somewhere else. Because as you know, in mechatronics, there's not a lot of textbooks out there for the courses that we teach. And it's like
Right.
you feel a little bit like Frankenstein, cutting pieces from here and there and sewing them together. So, in this case, I built everything from scratch, but found ways of some freely available resources that could supplement what they're seeing from me in the lecture.
Okay. So how do you see the future of this course? Do you think having it as a discussion topic maybe in our community could help expand upon this? Because similar to me, I'm sure there are a lot of instructors out there who would like to provide more in-depth programming experience for their students, but they're not necessarily computer scientists.
Right.
So which portions do you think could be added to this course, and how do you envision the ideal case for this course in the future?
Right. Well, you make a good point. Most engineers are pretty serviceable programmers, but it's not their specialty. Luckily, coding has always been something that I've pursued my entire life since I was very young. So it's nice that it comes naturally to me. Now, interestingly enough, now that I'm chair, I'm not teaching as much anymore. And I taught this course probably for the last time this past fall. And I recruited a computer scientist actually to be a part-time instructor for us who's doing that course right now. So she sat in on my lectures all last year, and she's actually been teaching some of the lab sections for the last year or so. And so now I've sort of handed the baton off to her that she's teaching the full course now as a computer scientist. So I've got a computer scientist teaching this course, and we've been able to get her up to speed on the hardware and those pieces in the lab. So that's the way I've solved that, by getting a computer scientist in on this. If you don't have that luxury, I think at the very least you can take the labs, which, I mean, my courses are all open source. I'm happy to share, my lab descriptions and everything, whoever is interested in them. You can take the labs, and if the students aren't really strong programmers, you can build them in such a way that you sort of help them more, and you give them sort of a skeleton code, and you have some pieces for them to change. You can present those labs to them where they have enough of it pre-made that they just have to fit the pieces together and maybe add some of the code. So I think there's a way for you to make them accessible to students that are not yet strong programmers.
I see. Thank you. So coming back to your program, just moving a little bit further back from this course, so your Mechatronics Engineering program. One of the questions that we got here was about design experience. So obviously different departments have that senior design course, but do you think the senior design that you have in your program is sufficient for to give the students a good hands-on skills for designing mechatronic systems?
I am not 100% sure of that. I mean, the one thing we do in our senior design is that every project must have a physical demonstration at the end of the semester of a working physical prototype. One of the pieces they do in the beginning of their senior design is they have to develop their minimum success criteria, and that happens maybe a third of the way through the semester, where they have to identify what their minimum success criteria are. And then if their physical working prototype at the end of the semester does not meet those criteria, they will not get cannot get a C in the class. So in that sense, there is a very significant design component that they have to, build something real and integrate the system and make it work. So in that sense, I'm very happy with our senior design there, but I am not convinced that that one experience is really enough. In our Intro to Mechatronics course, it does happen in the very first semester, but even there, they have some robotic challenge that they're given, and they have to conceive of a solution, build that solution, test that solution, and code that solution to be able to work. So there's a small design experience there. I think outside of creating another design course, which is quite popular, and I've seen that work well, where, say in the sophomore year, you have a true design course. I think that could work well. We haven't chosen that. But if you don't have that second design course, you can make some of your labs in your lab courses be more open-ended, and not telling them all the things that they're going to run into, and where they're going to have to make some design decisions in there. But that's a good question. That's something I think about too, of how we can make sure that there really is enough design in there, because that is definitely something you want to keep track of.
Right, right. So one other question that I had was in regards to programming specific for mechatronics and robotics engineering. So if you were to kind of outline the most important topics that you think a programming course specific to mechatronics and robotics should have, what would they be? So of course we have those fundamentals, right? There's always iterative structure, there's also conditional, sequential, but what else do you think is sufficient to put in a programming course specifically for mechatronics and robotics?
Right. The piece that I really think is important is translating the mathematical model into code, and being able to see the results of that model. The students, like I was showing with that summation sign, and they might not see that connection of how that summation sign is really just a loop. And that's a really hard thing in this course. The students have taken their first computing class, and they're asked to make this little list or whatever, but there's no math involved in there. And getting that connection of the mathematics and how that appears in a different form, but in the coding, that to me is really important. But even on the looping and that structure, one of the things I find students are weakest on are nested loops, and understanding I've got a loop inside a loop. And you learn that in your Computing 1 course, but why do you need that? You need that here because, first of all, you need a loop to calculate this summation, and then you need a loop because you need to calculate m's for different points. And hammering that home, how those looping structures fit together with some concept of a model, either mathematical or engineering or otherwise, that to me is the important piece, trying to get the students to see how they can use the computing to understand this mathematical model better and visualize it and understand it.
Okay, okay. So we have another question, which looks like our audience so loved your presentation as much as I did. And the question is about how they can get in touch with you, and how can we basically get this conversation going? How can we continue this conversation? And sure. I was going to ask you if it would be okay with you if we post something about this on our forum, so that we can have an ongoing conversation there. And also, if you mentioned that you have your courses as open source, so if you could please share some documents with us so that we can put them on our repository. I think that would also be helpful for other instructors out
Absolutely. There. Email me, call me. I will send you, my lab descriptions. All of my lectures are recorded. I have a public YouTube channel that has the recordings of the lectures from this course that everyone's welcome to have a look at. I love developing this material, and if it can help someone else, man, I'm all for that. So I'm happy to share, and call me or email me if you've got questions. I'm happy to learn from you and share whatever I have.
Great. Thank you very much. Yeah, once again, thank you for this great presentation. We will create a link to this topic on our forum so that everyone can come there and ask their questions or provide input. and I'm hoping to have courses like this established in more universities so that mechatronics and robotics engineering students can get the required expertise. So last but not the least, I wanted to encourage everyone, for those of you who are not already members of our website, mechatronicseducation.org. Go there, check out different sections. We have announcements about upcoming webinars and workshops. So we held our first workshop on the future of mechatronics and robotics engineering back in September. We are going to have 3 more workshops. The next one is going to be at Robotics Summit and Expo. We're going to have another one at ASEE and one more after that. And we're going to post announcements about each of these on the website. And similar to our first workshop, we will have support, financial support for the participants. So definitely, if you're interested, definitely reach out. We will have application links so that you can apply. And with that, I want to thank everyone again for participating in this webinar. Stay tuned for next webinars from our webinar series. We are going to, the recording for this presentation will be available, and we're going to send it out to all the people who registered here. And I hope you have a great weekend, and thanks again. And thank you, Dr. McFall, once again for this great presentation.
You're most welcome. It was my pleasure. I hope to hear from all of you in the future.
Thank you.